When we're writing exponential function rules from tables, we need to find two pieces of information from the table. We need to find the start value A and the growth factor B. To find the start value A, we do exactly what we did when we were looking at a linear table. We look for the row where x is 0, and the start value is just the value of y, or f of x, in that row. For a linear table, we then looked for the rate of change. We looked for how much we were adding or subtracting to y when x was going up by 1. Now we still need x to go up by 1, but now we're looking at what we are multiplying y by in order to go from one row to the next. Let's look at an example. In this first example, x is years and f of x, or y, is the number of bears. To find the start value, we look for the row where x is 0. In this case, that happens to be the first row, but that will not always be the case. So look for the row where x is 0. The start value, A, is just the value of f of x in that row. So A is 3 here. We start with 3 bears. Now to find the growth factor, we need to make sure that the table is going up by 1, which it is. Then we need to see what are we multiplying y by to go from one row to the next. Well, I can just eyeball that looking at this first row. What do I multiply 3 by to get 15? Well, I multiply 3 by 5. I even know that to get from 15 to 75, I multiply 15 by 5. My growth factor then is 5. If I weren't able to just look at the table and see, hey, I'm multiplying by 5, I would use division. So using division allows me to figure out what am I multiplying by 3 to get 15. So I start with a row, for example, 15, and I divide that value of f of x by the previous value. 15 divided by 3 tells me what I'm multiplying 3 by to get to 15. That's going to be the same as the value of 75 divided by 15. That's going to be the same as the value of 375 by 75, as well as the value of 1,875 divided by 375. Each of those division problems will give us an answer of 5. My growth factor is 5. To get from one row to the next, when x is going up by 1, y is multiplied by 5, times 5, times 5, times 5. I can now write my function rule because I know A and I know B. To write my function rule, I write f of x equals 3 times 5 to the x power. My variable is in my exponent. That's what makes this an exponential function rule. Next example. Start value. Again, the first row of the table, but not always. I look for x equal to 0. My start value is the value of f of x, 12. Now since x is going up by 1, I look to see what's happening to f of x. And I can see here I'm multiplying by 3 times 3 times 3. If you can't tell that looking at the table, do some division. Take a row, 36, and divide it by the value of f of x in the previous row. The growth factor is 36 divided by 12, which is 3. 108 divided by 36 is also 3. 324 divided by 108 is also 3. Function rule, f of x equals a, which is 12, times the growth factor 3 to the x power. I could have written this as f of x equals 3 times 5 to the x. F of x equals 12 times 3 to the x. That is fine. If that's more clear to you, that is perfectly acceptable. Last example. Start value. Dang it, again in the first row. I should have given you a different example. But we're not looking for the first row. We're looking for the row where x is 0. The start value is the value of f of x, which is 10. Growth factor, let's pretend that I can't see what I multiply by 10 to get 20. I'm going to divide 20 by 10. My growth factor is 2. This is a great table though, because I can definitely tell that 10 times 2 is 20, 20 times 2 is 40, and 40 times 2 is 80. Function rule is ready to go. F of x equals the start value 10 times the growth factor 2 to the x power, where again, it's perfectly fine to write that as 10 times 2 to the x. This might be more clear to you that this is 10 times 2 times 2 times 2 times 2 times 2, and if you like this version better, that is completely fine.